Over the last couple of weeks, we've been talking about a lot of fundamental topics in physics. Starting with kinematics, we learned the relationship between position, velocity, and acceleration in time. Then we learned that the way that we made those accelerations was through applying some net force. And we used Newton's laws, particularly Newton's second law, to figure out how the acceleration of some object could change. We used Newton's third law to figure out how to apply forces to other objects. In our last unit, we learned about energy. And while there were some things that energetic analysis allowed us to do easier, other things we still had to rely on old topics. But what energy was able to allow us to do is to solve some large set of topics through a scalar quantity and figuring out how this scalar quantity changed by applying forces over distance, by doing work and the like, putting energy into a system, and then doling out what kind of energy took different forms once it was in the system. Now, it turns out that this next topic, the topic that we're looking at this week, is very closely related to energy. It is another vector topic, so doesn't have the convenience of energy, but it's something that holds much more steadfastly through lots of different problem sets. So last week when we were doing conservation of energy, and while we colloquially said conservation of energy, what we were really looking at was conservation of mechanical energy. There's lots of forms of energy that we didn't really know how to account for yet, whether it was thermal energy, whether it was sound, heat, light, radio waves, crumpling of some object, any of those things. If it took some weird non-mechanical form, we didn't know what to do with it. And so there's a large class of problems that we didn't know what to do. This is the week where we figure out how to use a slightly different topic and look at a wider class of problems. In fact, in our next video, in 5B, we're going to look at the topic of collisions. And I'll say it there just like I'll say it here. You can't do a collision problem without doing momentum, particularly conservation of momentum. So if you try to do a collision problem without taking account of what we talk about this week, you are doing it wrong. You can't do it any other way. And so what I'd like to first talk about in this video is what this new topic, this new quantity is, momentum, and figure out what a new conservation of momentum law might look like, how momentum as a topic is related to some things that we have seen in the past, and maybe figure out how to put this new quantity, like energy, but different, into a system. Is there a momentum equivalent of work? Okay. So as we get started, let's go to OneNote here quickly. And we see that if you really trust Newton's second law, something that we looked at back in Unit 3, it said that the net force on some object is going to lead to that object's acceleration. And if you know the mass of that object, you can figure out what the acceleration is going to be. But the way we look at Newton's second law, and the way we looked at Newton's second law back in Unit 3, is not really what Newton said. What Newton actually said is that it is something much more closer to a different quantity. So I'll get there in just a little bit. So instead of talking about acceleration with this a that's shown here, let's instead talk about velocity and the change in velocity with respect to time, which is what acceleration is. So if you believe that the net force on some object leads to that object's acceleration, the acceleration is just the change in velocity with respect to time, so it can be written slightly differently. Now this looks like part of a chain rule. And if we have this product rule where we're taking the derivative of two things multiplied together, in this case the mass and the velocity, you would colloquially say from calculus that you're taking first times derivative of second plus second times derivative of first. So if we were to write out that whole product rule here, we could just as easily add this other term, where we have a change in momentum with respect to time, or change in mass with respect to time, sorry, times the velocity mass times the change in velocity with respect to time. So this looks like a first times derivative of second, second times derivative of first. Only if the mass of our object doesn't change with respect to time, what we are adding is a 0 right here. And we can add 0 to whatever we want without changing anything. But adding this 0, or expression for 0, allows us to change this quantity right here and write this quantity together. This new quantity, mass times the velocity, is something that today we call momentum. Newton called this a generic quantity of motion. So in this sense, what Newton really said is that if we have a net force, it would change this quantity of motion with respect to time. In other words, not only is the net force equal to mass times acceleration, but the net force is equal to the change in momentum with respect to time. These are the same thing. This is how it all works. Okay, so that's useful. Well, what do I mean by this thing called conservation of momentum? Okay, well this is actually related to Newton's laws also. It's actually more closely related to Newton's third law. That's totally fine. But basically what it's saying is if we have two objects that are interacting with each other, they're putting a force on each other. And this could be from a variety of different things. Later in the term, this could be due to gravitational effects. These could be connected by a spring. They could be connected by a string. But one object is putting a force on some other object. So in this particular scenario, we see that M1 is attracted to M2 with force 2, 1. M2 is attracted to M1 with force 1, 2. And because M1 and M2 are interacting with each other, those forces are a force pair from Newton's third law of force pair. So Newton's third law says if I was to take those two forces associated with the force pairs and I'd add them together, that has to be equal to 0. This is the same thing as force of object 1 on object 2 is the same as the force of object 2 on object 1. The same magnitude, opposite direction. So I'm just basically moving one of those terms to the other side. If I add those two forces together, I have to get 0. Now, what are these two forces? Okay, well, force 2, 1 is mass 1 times the acceleration of 1. Force 1, 2 is the mass of 2 times the acceleration of 2. These are the same thing. And if I was to now rewrite these accelerations in terms of changing velocities with respect to time, these velocities don't even have to be collinear. These velocities can be in random weird directions, as is illustrated here. But taking these two terms and once again adding those form expressions for 0 by taking the changing mass with respect to time and adding them in here, what we see is we have a change of M1 V1 with respect to time, a change of M2 V2 with respect to time. They have to be equal to 0. And, these masses aren't 0. These velocities aren't necessarily zeros. What has to be true is this total quantity of M1 V1 plus M2 V2 has to be equal to 0. It cannot change with respect to time. So the time derivative of these things has to be equal to 0. This quantity of the total momentum of a system has to be something called conserved. It's not going to change unless you come up with some way to add or remove momentum from the system. So remember once again that the momentum, usually indicated by the letter P, is the mass times the velocity. What this means is that the total momentum of a system does not change as a function of time. Once you have momentum in a system, it is a constant. So this all came about because of our trust and faith in Newton's third law. Part of our proof was using Newton's second law. This is a statement of our confidence and faith in Newton's laws. We believe that Newton's laws are true, and that leads to this quantity called conservation of momentum. Momentum can be carried in lots of ways, but the total amount does not change unless acted upon on the outside by some force. So this is conservation of momentum, just like we had conservation of mechanical energy in the past. Once energy is put into the system, it can take a variety of different forms, but it was all conserved in the system. If we wanted to change the energy of that system, we had to do work. Now, this is another conservation law. Once we have momentum into the system, maybe it can go into a couple of different forms and do a couple of different things. But we also have to talk about how we get momentum into a system. How did we do that? And that's what's here on the next page here with impulse. Impulse is a momentum equivalent of work. We use work to put energy into a system. We use impulse to put momentum into a system or take momentum out of the system. So, if you really believe this more Newtonian version of Newton's second law that says that the net force is the change in momentum with respect to time, we can certainly rearrange these terms. By moving the dt over to the other side, we see that a differential momentum is associated with a net force times the differential time. And if we wanted to find the change in momentum, we have to integrate net force over some time. Now, this is very similar to what we saw with work. With work, we were integrating net force over a distance. Here, we are integrating net force over a time. And they're not exactly the same thing. In fact, if we were thinking to ourselves, I see some object on an air track, or I see some object on a table, and I want to push it, yeah, I probably have some feeling for how I'm applying force over a distance. But more likely what's going on in our head is I'm applying force for a certain time. What's more intuitive to us is applying impulse to an object and not applying work to an object. Integrating this quantity with respect to time is much more natural to us, And that's mainly because all we've been doing all semester is looking at, how does force change as a function of time? How does position change as a function of time? How does velocity change as a function of time? How does acceleration change as a function of time? This relationship to time is really deeply ingrained with things that we've done all semester long. Right? So seeing how we integrate a force over a time instead of over this more arbitrary distance is more intuitive. But this thing, integration of force for a time, is something that is called impulse. Now, just to put in our heads in a more graphic way, when we are calculating work, we are integrating the area under a curve of a plot of force as a function of x. When we are doing impulse and adding momentum to a system, we are finding area under the curve of force as a function of time. So they're related to each other. Each of these things is going to change the motion of an object. So from the work kinetic energy theorem, if we are doing net work on an object, we are changing that object's kinetic energy. So to change kinetic energy, we have to be changing velocity, right? Similarly, if we are integrating force over a certain time, putting momentum into the system, it turns out that, momentum is just m times v. If the mass of that object isn't changing, doing this impulse on a system is also changing the velocity. These two things have to be related to each other in some way or another. So, that being said, we can probably more realistically think about what's going on. More realistically think about what's going on if we were to try to stop an object or start an object going. So let's say, for example, we have this 2 kilogram object moving at 10 meters per second, and we would like to stop the object. There are a variety of ways that we could do this. I mean, for one, we're trying to take energy out of the system. So most likely a force that we are applying has to be applied over some certain distance as this thing slows down to sap the energy out of the system. But we also have to apply a force over a certain amount of time. And that's more intuitive to us. And so looking at this, if we need to take some momentum out of the system, we need to apply an impulse. We need to apply a force over a time. And if we wanted to, we could apply a large force, say here 10 newtons over 2 seconds, to get an area under the curve of 20 kilogram meters per second. Or we could apply some smaller force, 5 newtons, but apply it for a longer time. This is also 20 kilogram meters per second squared. This is a way for us to take that momentum out of the system. And so what we often do with these analyses of conservation of momentum and using impulses rather than work to stop objects is we might be trying to change the time of a collision. Collisions are something that we're going to talk about more completely in our next video. But let's say what we wanted to do is lower the force associated with some collision. I don't want to be hurt as badly. These forces could damage me, lead to a lot of accelerations. Our bodies aren't built for that. So one thing that we can do is try to extend the time of a collision. If we make a collision last longer, smaller forces are needed. And this is what crumple zones on cars are doing. This is what airbags are doing in your car. They're trying to extend the time of collision, and not just your head hitting the steering wheel, but your head slowing down more gradually because it first interacts with this airbag and is allowed to slow down before it hits the wheel. It extends the time of the collision, lowering the force that is applied to you. And because the force is being lowered, the acceleration is lowered. Your bodies handle these lower accelerations better. And so that being said, that's kind of interesting. Now, as we already noted, there is a relationship between momentum and kinetic energy. If we were to put impulse into a system, we're going to be changing velocities. If we put work into a system, we're changing kinetic energies, which implies that we're also changing velocities. So these things have to be linked together in some way or another. So let's say we were to take our more trusted form of kinetic energy, 1/2 mv squared. There's nothing that says that we can't multiply this by a fancy form of 1, mass divided by mass. That's what goes on in this next line. So I multiplied the top by mass, I multiplied the bottom by mass. I'm just multiplying by a fancy form of 1. That's it. But what we now have on the top of this expression is the momentum of the object squared. So apparently the kinetic energy is related to the momentum in this particular way. If you know what the momentum in your system is, you take it, square it, divide by 2m, that is the kinetic energy in your system. Or rearranging terms, if you happen to know what the kinetic energy is, you can find the momentum by algebraically solving this exact same expression. Momentum is going to be the square root of 2m times the kinetic energy. And these two things go hand in hand all the time. And while the momentum and the kinetic energy in an object are related, they are not the same thing. If you know one, you can find the other. If you know the other, you can find one. But I want to talk a little bit about how changing the velocity of some object in a linear way is not the same thing as changing the kinetic energy in the same way. So let's say that we were trying to come up with we wanted to change the velocity of some object by some certain amount, right? And let's go to a piece of paper here just so we have something to kind of look at and talk about. I would like to change the velocity of a 1 kilogram object by 2 meters per second. Now, that being said, if we were looking at momentum stuff, we were looking at impulse stuff, I know that so this impulse is a change in momentum, right? And so the impulse being the change in momentum, it's mvf minus mvi, or it's m times the change in velocity. And let's say, for example, we wanted to go from VI equals 0 to VF equals 2 meters per second. We could certainly do that, and I see that a certain amount of impulse is needed to do that. The mass of the object is still 1 kilogram. It changes by 2 meters per second. It takes some certain amount of impulse to do this. 1 kilogram, 2 meters per second, 2 kilogram meters per second. But what if instead we wanted to go from VI equals 2 meters per second to VF equals 4 meters per second? Now this is the exact same change in velocity on the exact same massive object. And so in this scenario, we're looking at 1 kilogram. The change in velocity is still 2 meters per second. The impulse needed is 2 kilogram meters per second, just like before. J1 is equal to J2. Impulse did not change with this change in velocity that was asked. And so you would think to yourselves, well, is the same thing happening with kinetic energy? Well, let's see here. I know that with the case of kinetic energy, I wanted to see how much work is done, right? So work is going to be 1/2 m v final squared minus v initial squared. And this is a related thing, but this thing is not delta v squared. Delta v squared would be v final minus v initial quantity squared, and this is not the same thing as delta v squared. So if we were to look at the scenarios shown here, let's say we wanted to go from VI equals 0 to VF equals 2 meters per second. And we wanted to find out the work that was associated with this. Work 1 is going to be 1/2 1 kilogram. But now we've got 2 meters per second squared minus 0. And this is 4 divided by 2. This was 2 joules. It took me 2 joules of work to change the velocity by 2 meters per second, going from 0 to 2. So this was one setup. What if we wanted to do something akin to what we did over here, where VI is equal to 2 meters per second? We would like VF to be 4 meters per second. So we are changing the velocity. Now what we see is that we have 4 meters per second squared minus 2 meters per second squared. But 4 squared is 16, 2 squared is 4, and there's the units. We'll worry about the units later. 16 minus 4 is 12 divided by 2. This ends up being 6 joules. If we want the units, meters squared per second squared. Okay. So this ends up being 6 joules. This this impulse and this impulse are exactly the same. I'm changing the velocity by some certain amount. The mass of the object isn't changing at all. These two impulses are the same. But because of how kinetic energy works, the amounts of work that were needed to get these change in velocities are different. I had to do much more work here. So even if it was the same force that I was using, for example, in each of these two scenarios, here the force was applied for the same time. Apparently, they were not applied over the same distance. And this is maybe not too surprising from things that we saw from kinematic equations. If something is traveling very fast, it's going to be traveling over much more ground. So yeah, the force is applied over a lot larger distance, even if it's applied for a larger time when the velocities are big. So this difference between a linear relation of how the impulse is related to change in velocity and something much more complicated when it comes to work and energy is something to keep in mind. In fact, we might think to ourselves, if we were to go from 4 to 6, from 6 to 8, from 8 to 10, on and on and on, eventually it's going to take an infinite amount of work to change the velocity by even some incremental little bit more. And this is starting to hinge on a couple of things related to relativity that we will probably talk about if you continue on in modern physics. In some universities it's called General Physics 3. Because it turns out that we can't get things to an infinite speed. Eventually there's going to be a finite speed limit. And even if you were to put in an infinite amount of more energy, you can't get anything going faster than that. But you start to see some of the potential problems with the layout here. The way we fix that when we get to relativity is to do a slight tweak in how we talk about this Newtonian form of momentum. Momentum is slightly different than what we say here in a relativistic world, but this sort of gives the hints in where things could possibly break down and things that need to be concerned with for us. Now, that being said, I would also like to look at one more problem before we're done here. And so let's bring it up and just get an excuse to look at some of these problems. So here's a problem that allows us to do just a little bit of calculus. It's just a one-dot problem, so it's not the hardest thing that we're going to look at, but it's something for us to analyze. In the problem, we're told that at time t equals 0, this massive rocket in outer space fires an engine that exerts an increasing force on it in the x direction. This force obeys the equation f sub x equals a t squared. T is the time, and a is just some constant. Now we're told at a particular time what the magnitude of the force is. And because at a particular time we know a particular force, we can calibrate this constant a. So part A of the problem is asking us, okay, what are the units? What is this constant value of a? After that, we can do some other things, like finding out what impulse does the engine exert on the rocket during this time interval. How much does the rocket's velocity change during this interval? So we can look at some of these things. Now, first of all, if we're looking at part A, one thing that we know is a particular force at a particular time. And because of that, if we want to find out what the constant is, if it really is a constant, it has to be algebraically found like this. And because we know f and because we know t, we can pull out our calculator. And our force was 2150 and time was 1.2, or force here, 781.25, 781.25, and divide by 1.25 squared. Divide by 1.25 squared. Okay, nice and easy, 500. And this has to be units of Newton per second squared, because if I was to take this constant and multiply by some time in seconds squared, I have to get units of force. So if we need it later, we know what A is going to be. Good. Going back to the problem. Next, what impulse does the engine exert on the rocket during a 1.5 second interval starting at 2 seconds. So this is going to be from time 2 seconds to 3.5 seconds. So the definition of impulse is the integral of this net force dt, and we're going from t1 to t2. Now, what we were essentially told here is a start time and some interval of time. I can call that delta t, whatever this is. So delta t is 2 seconds, and t1 is 1.5, or t1 is 2 seconds, and delta t is 1.5 seconds. That's essentially what we're told. But we need to integrate that force, and the force as a function of time is a t squared. Has to be integrated over some time. So this is how we calculate the impulse. Now a is just a constant, and t squared integrated is going to be 1/3 t cubed. That needs to be integrated from our first time to our later time, like so. And here our later time is going to be 3.5 seconds cubed, and our initial time was 2 seconds cubed. So getting out our calculator, we've still got our 500. We can divide by 3. Okay, I'm going to just save this. We've got 3.5 cubed minus 2 cubed is equal to this time this thing that we just saved, which is what, 6,000? Let's call it 5810 kilogram meters per second. Okay. So that is the impulse that was done. Going back to the problem, how much does the rocket's velocity change during this interval? So we're looking for change in velocity. This impulse is mass times the change in velocity. That's the thing that we're looking for. J we've already found. Mass is given to us in the problem. So we just divide this number that we just calculated by the mass 2150. And we see that it changed by 2.70 meters per second. Through this process. Okay. Now, this is just one quick example. There's certainly other things that you can do with the concept of momentum. We're going to be doing a lot of it in our next video, but this is a good place to stop for now. I think you're really going to want to pay attention to our next lecture, the one that's on collisions, because it's really the heart of this whole thing.